Let me ask you something. When you hear the words nuclear bomb, what do you imagine? Most people picture a gigantic explosive, something like TNT, but far more powerful. A bigger bomb, a bigger fireball, a bigger shock wave. That sounds reasonable, but it is completely wrong. The difference between TNT and a nuclear bomb is not just size. It is the kind of energy being released. When TNT explodes, the atoms remain intact. They simply rearrange themselves in chemical reactions and release a little energy from their electron bonds. But a nuclear explosion goes much deeper than chemistry. It reaches into the nucleus at the center of the atom, and that tiny nucleus hides an astonishing amount of energy. In fact, the energy locked inside matter is so enormous that even a tiny bit of mass can release incredible power. Something first revealed by Albert Einstein. Once you see that, the real mystery becomes clear. Why does ordinary matter contain so much energy? Now, before we talk about nuclear bombs, I want you to think about something much more familiar. Ordinary explosives. Things like gunpowder or TNT. Because if you really want to understand why nuclear weapons are so powerful, you first have to understand what normal explosions actually are. Most people imagine an explosion as something mysterious or violent that simply releases a lot of energy. But in physics, the mechanism is actually quite simple. When a chemical explosive detonates, the atoms themselves are not destroyed. Nothing inside the nucleus changes. The atoms are still the same atoms after the explosion as they were before. What actually happens is that the atoms rearrange themselves into new molecules. Chemical bonds break and new bonds form. During that rearrangement, a small amount of energy is released. Let me give you an example. Imagine molecules inside a block of TNT sitting quietly together. Each molecule contains atoms connected by chemical bonds involving electrons. These bonds hold the atoms in a particular structure. When the explosive is triggered, those bonds suddenly break apart and the atoms rapidly rearrange into different molecules, such as gases. This rearrangement releases energy that had been stored in the chemical bonds. Now, the interesting thing is that each of these reactions releases only a tiny amount of energy. On the scale of a single molecule, the energy is almost insignificant. But here's the trick. In a real explosive, there are an enormous number of molecules packed into a small space. When the reaction begins, it spreads through the material extremely quickly. Billions upon billions of molecules react almost simultaneously. The combined energy from all those tiny reactions adds up to something powerful enough to create a violent explosion. But even though this looks impressive, the amount of energy involved in chemical reactions is actually quite limited. And the reason is simple. Chemistry only deals with the outer part of the atom. It only involves the electrons that move around the nucleus. Those electrons are held in place by electromagnetic forces that are relatively weak compared with the forces that exist inside the nucleus itself. So when TNT explodes, we are really only rearranging the outer structure of atoms. The nuclei of the atoms remain completely untouched. The protons and neutrons inside the nucleus stay exactly where they were. And because the nucleus contains almost all of the mass of the atom, the enormous energy hidden there never participates in the reaction. You can think of it this way. Imagine you are holding a large steel safe filled with gold bars. But instead of opening the safe, you are only moving around the paint on the outside of it. That is roughly what chemistry does with atoms. It rearranges the outer layers, while leaving the much more energetic interior completely untouched. This is why all chemical explosives share a similar limit in their power. Engineers can design better explosives by packing molecules more efficiently or by allowing reactions to spread faster. But no matter how clever the design becomes, the energy still comes from chemical bonds. And chemical bonds simply do not store very much energy compared with what exists deeper inside matter. That difference becomes crucial when we compare chemical explosives with nuclear reactions. In nuclear reactions, the nucleus itself changes. Instead of merely rearranging electrons, the reaction alters the structure of the atomic nucleus. And the forces holding the nucleus together are enormously stronger than the forces involved in chemistry. So the first step in understanding nuclear weapons is realizing something very important. TNT and other explosives are not weak because humans have not engineered them well enough. They are limited because chemistry itself only accesses a tiny fraction of the energy hidden in matter. And once you begin to look inside the nucleus instead of the electrons, you suddenly discover that the energy available there is not just a little larger, it is millions of times greater. Now let me take you a little deeper into the atom, because this is where the story really becomes fascinating. When most people imagine an atom, they picture something like a tiny solid ball, a little particle that cannot be divided any further. That was actually how scientists once imagined atoms long ago. But modern physics reveals something far stranger. An atom is not a solid object at all. In fact, an atom is mostly empty space. Imagine enlarging a single atom until it becomes the size of a large sports stadium. If you could stand in the center of that stadium, you might expect to see matter everywhere around you. But that is not what you would find. The electrons would be moving far away from the center like tiny particles traveling through the enormous space of the stadium. And at the very center you would find something incredibly small, something almost unbelievably tiny compared with the size of the atom. That tiny object is the nucleus. If the entire atom were the size of a stadium, the nucleus would be roughly the size of a marble sitting at the center. Almost everything else in the atom would be empty space. This discovery shocked early physicists because it meant that matter, which feels completely solid to us, is actually built from structures that are mostly emptiness. But here is the remarkable part. Even though the nucleus is incredibly small, it contains almost all of the mass of the atom. The electrons contribute almost nothing to the mass. Nearly the entire weight of the atom is concentrated inside that tiny nucleus. Inside the nucleus, there are two kinds of particles. There are protons, which carry positive electric charge, and there are neutrons, which carry no charge at all. These particles are packed together extremely tightly in a space so small that it is difficult to imagine. Because they are so close together, the forces acting inside the nucleus must be extraordinarily strong. You might expect the protons inside the nucleus to push each other apart because they all carry positive electric charge. And objects with the same charge repel each other strongly. If only electric forces were acting, the nucleus would instantly fly apart. But it does not, because something even stronger holds the nucleus together. That force is called the strong nuclear force. This force is one of the fundamental forces of nature, and it is incredibly powerful over very short distances. When protons and neutrons are extremely close together, this force pulls them toward each other with tremendous strength, strong enough to overcome the electrical repulsion between the protons. In a sense, the strong nuclear force acts like an invisible glue that binds the nucleus together. Now here's the key idea that matters for our story. When protons and neutrons are locked together by this powerful force, they are holding a huge amount of energy inside the structure of the nucleus. You can think of the nucleus almost like a tightly compressed spring. As long as the spring remains locked, the energy stays hidden and nothing dramatic happens. But if the structure of the nucleus changes or breaks apart, that stored energy can suddenly be released. And the energy stored inside the nucleus is vastly greater than the energy stored in chemical bonds between atoms. Remember that chemical reactions involve only electrons moving around the outside of the atom while the nucleus remains untouched. But the forces acting inside the nucleus are enormously stronger than the forces that hold electrons in place. That means when the nucleus changes, the amount of energy involved is dramatically larger. So the difference between chemical explosions and nuclear reactions becomes very clear. Chemistry rearranges atoms but leaves the nucleus exactly the same. Nuclear reactions change the nucleus itself. Because the nucleus contains nearly all of the mass and energy of the atom, the consequences of those reactions are far more dramatic. In other words, the reason nuclear bombs are so powerful is not simply because they involve special materials. It is because they unlock a deeper layer of energy hidden inside matter itself. The energy stored in the tiny nucleus at the center of every atom. Now that you and I have looked inside the atom, the next step is to understand something even more surprising. The energy that holds the nucleus together is enormously larger than the energy involved in ordinary chemistry. And when I say larger, I do not mean 2 times larger or 10 times larger. I mean millions of times larger. This difference is the real reason nuclear explosions are so powerful compared with chemical explosives like TNT. Let us start with the kind of energy that chemistry deals with. When atoms form molecules, the electrons around those atoms create chemical bonds. These bonds hold atoms together in structures like water molecules or the molecules inside explosives. Breaking those bonds or rearranging them releases energy. That is what happens when fuel burns or when TNT detonates. But the amount of energy stored in a chemical bond is actually very small. On the scale of a single molecule, it is tiny. You only notice the energy because enormous numbers of molecules react at the same time. Inside the nucleus, something completely different is happening. The particles inside the nucleus, the protons and neutrons, are held together by the strong nuclear force. This force is vastly stronger than the electromagnetic forces that control electron bond. When nucleons are bound together inside the nucleus, they are locked into a configuration that contains a very large amount of binding energy. Binding energy is simply the energy required to pull the nucleus apart into separate particles. Here is the important point. The amount of energy needed to separate nucleons from the nucleus is enormously larger than the energy needed to break chemical bonds between atoms. If you compare the numbers, the difference is staggering. Chemical bond energies are typically measured in electron volts, while nuclear binding energies are measured in millions of electron volts. That means nuclear interactions involve roughly 1,000,000 times more energy than chemical ones. You can think about it in a simple way. Imagine 2 systems that are both held together by springs. One spring is very soft and easy to stretch. The other spring is incredibly stiff and tightly compressed. If both springs suddenly snap, the second one will release far more energy. Chemical bonds are like the soft spring. Nuclear forces are like the extremely compressed spring hidden inside the nucleus. Physicists discovered something interesting when they studied nuclei across the periodic table. They found that nuclei have different amounts of binding energy depending on their size. If you look at a graph of binding energy per nucleon, you see a curve that rises for lighter nuclei and reaches a maximum around elements like iron. This graph is called the binding energy curve, and it reveals something profound about nuclear reactions. For very heavy nuclei such as uranium, the binding energy per nucleon is slightly lower than for medium-sized nuclei. That means if a heavy nucleus splits into 2 smaller nuclei, the resulting fragments are more tightly bound than the original nucleus. Because the final configuration has higher binding energy, the extra energy must be released during the reaction. That released energy appears as heat, radiation, and the motion of the nuclear fragments. This process is known as nuclear fission. When a heavy nucleus like uranium splits into smaller nuclei, the difference in binding energy is converted into usable energy. And because the nuclear forces involved are so strong, the amount of energy released is enormous compared with anything chemistry can produce. Let me give you a way to picture the scale of this difference. If you take 1 kilogram of a typical chemical explosive like TNT, it releases about 4 million joules of energy when it detonates. That sounds impressive, and it is powerful enough to destroy buildings. But if you take 1 kilogram of nuclear fuel undergoing fission, the energy released can be tens of millions of times greater. That is why a relatively small amount of nuclear material can produce an explosion comparable to thousands of tons of chemical explosives. So the key idea is this: chemical reactions release energy from electron bonds around atoms. Nuclear reactions release energy from the forces holding the nucleus together. Because the strong nuclear force is so much more powerful than the forces of chemistry, the energy involved is vastly larger. Once scientists realized this, they understood that the nucleus of the atom contains a reservoir of energy far beyond anything previously imagined. And learning how to release that energy changed both physics and human history forever. Now you might be wondering something very natural. If the nucleus contains so much binding energy, then where exactly does the energy of a nuclear explosion come from when the nucleus splits? It almost sounds contradictory at first. If the nucleus is held together by a powerful force, then breaking it apart should require energy rather than release energy. But the situation is a little more subtle. And this is where nuclear physics becomes very interesting. Let us look at what happens when a heavy nucleus, such as uranium, is disturbed. A uranium nucleus contains many protons and neutrons packed together in a delicate balance. The strong nuclear force pulls the particles together, while the electrical repulsion between the many positively charged protons tries to push the nucleus apart. In very heavy nuclei, these two effects are nearly balanced, which means the nucleus is only barely stable. Now imagine that a neutron enters the nucleus. Because the neutron carries no electric charge, it can slip into the nucleus relatively easily. When it is absorbed, the nucleus suddenly becomes slightly heavier and more energetic. This added energy can cause the nucleus to vibrate and deform. Physicists often describe this deformation using the analogy of a liquid drop. The nucleus stretches slightly and begins to wobble. If the distortion becomes large enough, the nucleus can split into two smaller nuclei. This process is called nuclear fission. When the split occurs, the two fragments push away from each other with enormous speed because the electrical repulsion between the many protons suddenly becomes dominant. But here is the crucial point. The two smaller nuclei that are produced are actually more stable than the original large nucleus. This difference in stability is connected to the binding energy we discussed earlier. The smaller nuclei have a higher binding energy per nucleon than the original uranium nucleus. That means the nucleons in the final fragments are held together more tightly than they were before the split. Because the final configuration is more stable, the extra energy must go somewhere. It is released during the fission process. The energy appears in several forms. Most of it becomes kinetic energy carried by the two nuclear fragments as they fly apart at extremely high speeds. Additional energy appears as gamma radiation and as the motion of neutrons that are also released during the reaction. All of this energy ultimately turns into heat as it interacts with surrounding matter. At this point, you might ask another question. If the energy comes from the difference in binding energy, why does that correspond to such an enormous amount of energy? The answer was revealed by one of the most famous ideas in physics. The relationship between mass and energy discovered by Albert Einstein. Einstein showed that mass and energy are actually two forms of the same thing. His famous equation, E equals mc squared, tells us that a certain amount of mass corresponds to a specific amount of energy. In nuclear reactions, something very subtle happens. The total mass of the final products is slightly smaller than the mass of the original nucleus and the incoming neutron. The missing mass has not vanished mysteriously. It has been converted directly into energy. This difference in mass is called the mass defect. Even though the amount of mass that disappears in a single fission event is extremely small, the multiplication by the square of the speed of light makes the resulting energy enormous. That is why a tiny change in mass inside the nucleus can release a tremendous amount of energy. In a single nuclear fission reaction, the amount of energy released is already millions of times greater than the energy from a single chemical reaction. But the real power of nuclear explosions comes from the fact that these reactions can happen again and again inside the same material. Each fission event releases additional neutrons, which can trigger further fission events in nearby nuclei. So the energy of a nuclear explosion ultimately comes from a very simple principle. Heavy nuclei like uranium are not in their most stable form. When they split into smaller nuclei, the new configuration is more stable and the excess energy is released. Because that energy is connected to a small loss of mass through Einstein's equation, the amount of energy released is extraordinarily large. What begins as a tiny change in the structure of a single nucleus therefore becomes a powerful release of energy when many nuclei undergo the same process at nearly the same time. And that is the fundamental reason a nuclear reaction can produce an explosion far beyond anything chemistry can achieve. Now, at this point in the story, you might start to see something very curious. Long before nuclear bombs existed, physicists already knew that matter contained enormous amounts of energy. In fact, the possibility had been predicted decades earlier by a remarkable idea from Albert Einstein. The idea appeared in a very short equation that later became one of the most famous expressions in all of science. E equals mc squared. Let us slow down for a moment and think carefully about what that equation really means. The letter E represents energy and the letter m represents mass. The constant c represents the speed of light, which is an enormous number, about 300 million meters per second. When Einstein squared that number, the result became unimaginably large. What the equation tells us is something quite astonishing. Mass itself is simply another form of energy. They are not separate things, but two different ways of describing the same physical reality. Before Einstein, most scientists thought of mass and energy as completely different concepts. Mass was the amount of matter in an object, while energy was something that caused motion or heat. Einstein showed that the distinction was not fundamental. If you have mass, you also have energy stored inside it. The equation tells you exactly how much energy corresponds to a given amount of mass. Now, here is the surprising consequence of that idea. Because the speed of light squared is such a huge number, even a tiny amount of mass corresponds to an enormous amount of energy. Let me give you a simple example. If you could somehow convert just 1 gram of matter entirely into energy, the amount of energy produced would be comparable to the energy released by many thousands of tons of TNT. That is an astonishing amount of energy from an amount of matter smaller than a sugar cube. When Einstein first wrote down his equation in 1905, he was not thinking about nuclear bombs. The equation came from his work on the theory of relativity and the deep relationship between space, time, matter, and energy. At the time, there was no known mechanism for converting mass directly into energy in any practical way. The equation was simply a theoretical insight into the structure of nature. But as physicists began studying the nucleus of the atom in the following decades, they slowly realized something important. Nuclear reactions actually do involve tiny changes in mass. When a heavy nucleus splits into smaller nuclei, the total mass of the products is slightly less than the mass of the original nucleus. That missing mass has not disappeared. According to Einstein's equation, it has been converted directly into energy. This is exactly what happens during nuclear fission. The difference in mass between the original nucleus and the final fragments is extremely small. But when that mass difference is multiplied by the square of the speed of light, the resulting energy becomes enormous. What Einstein had predicted as a theoretical relationship turned out to be the key to understanding the enormous power released in nuclear reactions. You can think of it in a simple way. Inside every atomic nucleus, there is a certain amount of mass that is effectively stored as binding energy. When the structure of the nucleus changes, that energy can be released and a small portion of the mass disappears in the process. The energy that emerges in a nuclear explosion is therefore not created from nothing. It is energy that was already hidden inside matter itself. This realization changed physics forever. It meant that ordinary matter, the material that makes up everything around us, contains vast amounts of energy locked inside its structure. Most of the time that energy remains inaccessible because the nucleus is extremely stable. But under the right conditions, nuclear reactions can unlock a small fraction of that energy. And that is the remarkable connection between Einstein's famous equation and the power of nuclear reactions. The explosions produced by nuclear fission are not mysterious sources of energy appearing out of nowhere. They are direct demonstrations of the deep relationship between mass and energy that Einstein discovered. Every nuclear reaction is a tiny confirmation of that idea. So when we say that nuclear bombs release enormous amounts of energy, what we are really saying is something even more profound. A small portion of the mass inside atomic nuclei is being converted into energy exactly as Einstein's equation predicts. And because the conversion factor involves the square of the speed of light, even a minute loss of mass can produce a truly extraordinary amount of energy. Now that we understand where nuclear energy comes from, the next step is to make a direct comparison between ordinary explosives and nuclear fuel, because numbers sometimes make the story much clearer. Let us begin with something familiar: TNT. TNT is one of the standard references scientists use when they measure the strength of explosion. When 1 kilogram of TNT detonates, it releases roughly 4 million joules of energy. That is a large amount of energy by everyday standards. It is powerful enough to destroy structures nearby and create a strong shock wave. But now let us compare that with the energy released by nuclear reactions. When a single uranium nucleus undergoes fission, the amount of energy released is about 200 million electron volts. That number may not sound meaningful at first, but when you convert it into ordinary energy units, you discover something remarkable. Each individual nuclear fission releases about 10 million times more energy than a typical chemical reaction between molecules. The difference becomes even more striking when we scale things up to real quantities of material. If you had 1 kilogram of TNT and detonated it, you would get those 4 million joules of energy we mentioned earlier. But if you had 1 kilogram of uranium undergoing nuclear fission, the total energy released could reach around 80 trillion joules. That is roughly equivalent to the explosive power of about 20,000 tons of TNT. This comparison reveals something extraordinary. A relatively small mass of nuclear material can release as much energy as thousands of tons of chemical explosives. That is why nuclear weapons do not need to be physically large to produce devastating explosions. The energy density of nuclear fuel is simply far greater than anything chemistry can provide. The reason for this enormous difference goes back to the structure of the atom. Chemical explosives involve only the outer electrons of atoms and the energy stored in their chemical bonds. These bonds are relatively weak, and the amount of energy they store is limited. Nuclear reactions involve the nucleus itself, where protons and neutrons are bound together by the strong nuclear force. Because this force is vastly stronger than the forces involved in chemistry, the energy stored inside the nucleus is correspondingly larger. You can think about the difference in another way. Imagine two systems storing energy. One system stores energy in small elastic bands stretched slightly between atoms. The other system stores energy in enormous compressed springs deep inside the nucleus. When both systems release their energy, the second one will obviously produce a much larger effect. Chemical reactions release the energy of the small elastic bands, while nuclear reactions release the energy of the powerful compressed springs inside the nucleus. This is why the destructive potential of nuclear reactions shocked scientists when they first understood the numbers. Even a small amount of mass converted into energy, according to Einstein's equation, produces an enormous amount of energy. In nuclear fission, only a tiny fraction of the mass of the uranium actually disappears. Yet the energy released is still comparable to the explosion of thousands of tons of TNT. Another way to see this difference is to imagine converting mass directly into energy. According to Einstein's equation, if just 1 kilogram of matter were completely converted into energy, the result would be about 90 quadrillion joules. That amount of energy corresponds to the explosive power of roughly 20 million tons of TNT. Nuclear reactions do not convert all of the mass into energy, but even converting a very small fraction produces astonishing power. So when we compare TNT with uranium, we are really comparing two completely different scales of energy. Chemical explosives release energy stored in the arrangement of electrons around atoms. Nuclear reactions release energy stored in the structure of the atomic nucleus itself. Because the forces inside the nucleus are so much stronger, the energy released is millions of times greater. Once you understand this comparison, the power of nuclear explosions becomes less mysterious. It is not that nuclear bombs are simply bigger explosives. It is that they tap into a deeper reservoir of energy hidden within matter, a reservoir so large that even a small amount of nuclear material can produce an explosion far beyond anything chemical explosives could ever achieve. Now, after looking at all these pieces of the story, I want you to step back with me for a moment and think about the deeper meaning behind all of this. Because the physics we have been discussing is not only about bombs or explosions. It actually reveals something far more profound about the nature of matter itself. The real lesson hidden inside nuclear physics is that the ordinary material around us contains an enormous amount of energy locked inside its structure. For centuries, people believed matter was something simple and solid. A piece of metal or a stone seemed like a stable object that simply existed in space. But modern physics showed that matter is not a static substance at all. Instead, it is a highly organized form of energy. The atoms that make up matter contain nuclei held together by incredibly strong forces. And those forces trap enormous amounts of energy inside a tiny space. What makes this idea so fascinating is that most of the time this energy remains completely hidden. The nuclei inside atoms are very stable. The strong nuclear force binds protons and neutrons together so tightly that the structure can remain unchanged for millions or even billions of years. That stability is why the world around us feels calm and predictable. The energy stored in matter stays locked away where we cannot normally reach it. But nuclear reactions reveal that this energy is always there, waiting inside the nucleus. When the structure of the nucleus changes, even slightly, some of that energy can be released. And because the energy stored in nuclear binding is so large, even a tiny change can produce dramatic results. This is why nuclear reactions are capable of releasing such enormous amounts of energy from relatively small amounts of material. This realization connects directly with the idea introduced by Albert Einstein. His equation E equals mc squared tells us that mass itself is simply another form of energy. What appears to us as solid matter is actually energy held together by the laws of physics. When a nuclear reaction changes the arrangement of protons and neutrons inside the nucleus, a small amount of that mass is converted into energy and released into the surrounding world. The same principle that explains nuclear explosions also explains many of the most powerful processes in the universe. For example, the enormous energy produced by stars comes from nuclear reactions occurring in their cores. Inside the sun, hydrogen nuclei combine to form helium in a process known as nuclear fusion. During that process, a small amount of mass is converted into energy and released as the sunlight that warms our planet. The energy that drives weather supports life and powers ecosystems on Earth ultimately comes from nuclear reactions happening deep inside the sun. So the power revealed by nuclear physics is not something unnatural or artificial. It is part of the fundamental structure of the universe. The difference is that inside stars, these reactions occur under natural conditions over vast scales of time and space. In human technology, we have learned how to trigger certain nuclear reactions much more quickly, which is why the energy can appear suddenly in the form of an explosion. When physicists like Richard Feynman explain these ideas, they often emphasize the sense of wonder behind them. The atoms that form everything around us, the air we breathe, the ground beneath our feet, and even our own bodies. All contain tiny nuclei where enormous energies are stored. Most of the time, those energies remain quiet and stable, hidden inside the structure of matter. But understanding that they exist gives us a deeper appreciation for the remarkable nature of the physical world. In the end, the story of nuclear energy is really a story about how deeply interconnected the universe is. The same laws of physics that govern the smallest structures inside the atom also govern the energy of stars and the evolution of galaxies. What began as a question about why nuclear bombs are stronger than TNT leads us to a much broader insight. Matter itself is a form of energy organized by the fundamental forces of nature. And within even the smallest pieces of the universe, there exists a tremendous hidden power waiting to be understood.